Hello and welcome back to this lecture 32 on biomicroelectromechanical systems. Let's quickly review what had been done last time. We talked about the principles of micro mixing and diffusion driven kinetics. I'd just like to reiterate that in the micro scale, mixing really is a diffusional phenomena. There is no as such other mass transport except intermolecular diffusion. And so therefore diffusion time and residence time and their comparison becomes a very important criteria for establishing proper mixing. We talked about active and passive micro mixers. Active mixers, if you may recall, are essentially those mixers where energy is being supplied externally by mechanical or non-mechanical means, and passive mixers are pure mixing by intelligent design, where you can actually split the flows apart many times and join them back so that they form laminae, and that way you reduce the interdiffusion length between the different mixing layers, and so therefore the time of diffusion can be reduced in this manner and taken much below the residence time, so that there is mixing till and until the flows reside in the chip, and by the time it gets out they are totally mixed. So we talked about parallel and sequential lamination mixers. Parallel mixers are where you will have multiple streams focusing on to a small cross sectional area, so that the diffusion length becomes equal to the actual length divided by n, where n is the number of such streams, and sequential being basically trying to go out of plane and then back in plane, so that you can physically laminate the flows together, and therefore there is a reduction in the diffusion time by about 4 to the power of n minus 1, where n is the number of stages where this mixing takes place. We also tried to do some numerical examples, designed a Y-shaped mixer, found out what is the length of the micro channel for the mixing to be spontaneous and proper. We also designed a meandering micro mixer and reduced it into a small 6 mm by 6 mm area, and tried to define number of turns that a channel of finite length would take if it comes into this particular area. Then we also talked about different designs for parallel and sequential lamination mixers based on this diffusion time reduction concept, and compared for a certain amount of mixing time ratio both the stages, and we found out certainly that in case of sequential lamination mixers lesser number of stages are needed in comparison to that in the case of parallel lamination mixer for proper mixing. Okay. So let us look at today a little more of experimental microfluidics, and I would like to discuss a small example here which is actually performed by graduate students, and essentially students starting new in this area were kind of left astounded by the counterintuitive nature of the microflows, and definitely they are much way beyond the concepts that you can have from the macro scale mixing or macro scale turbulence driven phenomena. So here in this design experiment we were supposed to design a 3-layered mixer with a glass layer at the bottom, okay, as you can see here, and this glass layer has been drilled with some holes so that you can have these holes for inlets and outlets of the fluid. You have another layer at the top of it which is actually a PDMS layer with a T section channel, as you can see here in the top view, illustrated in the top view, and here there is some sort of a continuous layer of PDMS at the top of these channels, so that they are covered, okay, they are replicated on the lower surface of the PDMS, and this then is bonded to this glass layer, okay. Then further you have another layer where you have these blisters, okay, the third layer, and in this particular layer again you have a certain thickness of PDMS over the blisters. The blisters, as can be demonstrated, are represented here, are actually air pockets, and this further is bonded back into the top of the first PDMS layer. Okay. So, you have a 3-layered or a stack of 3-layer devices, and here what you do is you use these ports for feeding in and out the fluid flow, and essentially you feed these particular ports here to inflate and deflate the air blisters, so that you can actually compress these channels on both ends here, as you can see here in this particular figure. So, here as you see, there are these 2 blister valves which would actually regulate the flow coming from these 2 inlets, input 1 and input 2. And the idea is that these 2, one may be dye, one may be water, and they may be mixing along this output here of the stream or outlet of the stream. They would be mixing along this this particular zone of the stem of a T, and in this particular T again you have an area which is unknown, and the idea was that the students in this particular experiment were supposed to design certain features and structures in this area, so that they could promote quick and rapid mixing in this particular architecture. So, several designs were proposed at the first instance by the students. The 4 most prominent designs which were proposed are tube bank like structures, where basically there would be small pits in this particular area, and this would be corresponding to small pillars of the PDMS which gets replicated on the top of this. So, this was one illustration where this central area here is introduced with this kind of a feature or a structure, and the flows go from the arms of the T and mix along this particular area which is also along the stem of the T. Similarly, here if you see in this particular example, you have let us say flows coming from both ends here and mixing along this circular area, which is essentially made up of small triangular pieces of resist, and if you just do the replication on the top of this, it becomes triangular pieces of PDMS pillars on the top surface of the reservoir, which is shown here in this particular example. Okay. The third design was a figure 8 type of system, where there would be a repeated amount of mixing and split ups of the flow. So, you have flow 1 and 2 coming from both these directions, and they would mix and they would split up again and then again mix, and so on and so forth. So, this is a figure 8 kind of design. And then in the fourth design, the students planned a meandering shaped micro mixer, where they would have all this fluid go lengthwise side by side with a certain interfacial area along a bigger track which is defined by this meandering channel between the small region on the stem of the T. So, all these 4 designs were investigated for mixing effects. A fluorescence dye was used from one end and it was gravity fed. The idea was, which was given in the constraint, that you should have the flow sources elevated to about 25 centimeters, which means that a pressure of equal to 2.45 kilopascals is to be generated, and after flowing this kind of a pressure driven flow through these micro channels, the following results came, and they were really counterintuitive. So, when you actually use these structures, whether it is the tube bank kind of structure or the triangular type, you have really, as you see here, the fluorescence dye and the water flowing parallelly. What is interesting to observe here is that although there are a lot of these small PDMS pillars around which the fluid should rotate and it should create local vortices or eddies, they are too small to cause any mass transport, particularly across the interfacial layer. So, even though there exists some eddies, some vortices away from the interface, they are not significant to contribute any kind of mass transport across the 2 layers, and therefore, until and unless you really start operating the blisters and block one flow at a time and try to move this cross section, as you are seeing here. In this case, the flow line with the dye has been pinched, and so the flow of the dye has reduced to one side, and similarly when the other inverse effect is done with the water line pinched, the dye would try to go. So, it swish past, the interface swishes past in a very serpentine like manner as you actually try to open and close the dye and the water one at a time through this automated blister set. and that does result in some amount of mixing, although not very appropriate. So the take home message here for the experiment was that even though you have structures and features which would cause the eddies to develop, they would be too far away from the interface, or there won't be much significant effect of these eddies and vortices away from the interface to cause the mass transport between the two streams. So a couple of things here to be mentioned. One is the flow velocity at the exit is roughly about 2.84 millimeters per second. That is how it was defined, and corresponding to that the Reynolds number was really low, about 0.00186. So this is without valving, and this is with valving. The other two designs also were evaluated. The figure 8 type design basically would be something like a parallel lamination mixer, and as we all know, in the case of parallel lamination mixer, the time nu would be actually equal to 1 by n square times of old time, right, and n and 2 in this case, and d essentially in this case is about 10 to the power of minus 4, it being a fluid. Okay. So if you see here, this kind of illustrates how these fluorescent dyes would behave with water. You can see there is some portion of the dye, a stream of dye, which actually goes in here in the second illustration, and similarly we find that there is a component of water which goes in this second illustration here. The new diffusion time after splitting is about some numerical constant k times about 10 to the power of 4 seconds. Okay. In this particular case it is much greater than the residence time of the two streams. K has been calculated to be about 3 to 4 seconds in our particular case. So there is no mixing though, but then there is a lamination effect which is created, and there is some streaks of dye which goes into the water side and some streaks of water which goes into the dye side, particularly in the second junction, which is pretty much what we expect in case of a parallel lamination mixer. The only design which worked in our case in this particular experiment was the serpentine design. You can see this design here, although I do not have the mixing illustrations in this particular slide. But then what effectively we observed here is that there would be an interaction between the green dye and water if you pass it through a serpentine length, and one of the reasons that is so is because we think that the interfacial area, which is also proportional to the mass transport at a constant flux of diffusion, being more in this case because of more length of the serpentine, would promote a mass transport rapidly between the two flowing streams. Okay. And this rapidity of mass transport continues for a longer time because of the meandering shape and the long length of the channel. So you are actually trying to recite the flows for a longer time, so that this overall interfacial area gets significantly higher, and we did see some mixing at this end here in this particular kind of illustration or design. So some other examples, this has been quoted from this paper by Renier et al. From Purdue, who talks about how you can actually introduce novel structures in order to promote mixing. Here, as you can see, there is a small amount of fluid being kind of taken away from this flow path and being put into the next zone here as laminae or bands. Okay. And as you go along, this is really a very rapid form of micro mixing that can happen. Okay. So although in all these structures, novel structures using these different concepts from hydrodynamics, the mixing principle is really only diffusion. Okay. This is another example by Jaeger et al. Which talks about the separation or particle separation just by using a microfluidic setup without any filtration mechanism here or without any membrane. So here the concept is very simple. As we know, the diffusion length x square that a molecule would traverse is also proportional to the diffusion time, and the constant of proportionality is 2d, where d is the diffusion constant. So if you really calculate the value of d, it depends on several factors like the size of the molecule, okay, the viscosity of the medium, and this kBT is basically Boltzmann constant into temperature T of the particular medium. And so if suppose diffusion constant is given in this manner, and you have a diffusion constant higher in case of one species and lower in case of the other species, then by virtue of equality here the distances that it may have to move would be much higher in the same kind of time, okay. And so therefore the velocity of a heavier molecule, the one with diffusion coefficient more, the velocity of the molecule with a higher diffusion coefficient is definitely more, okay. Also interesting is the fact that lighter the molecule is or lesser the size of the molecule, more would be the diffusion coefficient. So biotin in this case is much smaller in comparison to albumin, which both of them are proteins essentially. And so because of its smaller size, the diffusion constant in case of biotin is about 350 micrometers square per second in comparison to albumin, which is about 65 micrometers square per second, so about 1/5. So the size effectively is also about 5 times in case of albumin. So smaller molecules diffuse faster, that is a very natural tendency, and this effect can be in principle used for separation. How? Let us say you have two fluids here. This is a buffer solution which you are running through this particular channel, and there is also some kind of a mixed solution which you are running here essentially from this end. And the idea is that as the flow goes past this, there is a phase separation, because the idea is that the heavier molecule will not be that mobile in comparison to lighter molecule. Lighter molecule here, as we assume, would diffuse towards this end actually, okay, will flow in this direction. And so assuming that to happen, the ones which are left behind in this yellow region, as you can see, are the heavier molecules. So the heavier molecules typically go out where the lighter molecules can be separated and can be extracted as carried by or transported by this buffer at this particular end. So therefore smaller particles diffusing further will kind of get separated from the stream by virtue of a higher diffusion constant or a higher velocity in comparison to the smaller size particle. So you can use these mechanisms really for particle separation, okay. Another interesting example of where what microfluidics can do comes from this paper by Bitensky et al., where they talk about a biomimeric auto separation of leukocytes. Leukocytes are if you compare the sizes are pretty much higher in size or diameter than the most abundant species inside the human blood, that is red blood cells. If you look at really human blood contains a plasma. Plasma is again bunch of ions present in solution. This is the liquid plasma, so you have different salts and waters. About proteins 52 to 57% by volume, which is immersed species in this plasma are platelets, which are about 250,000 to 400,000 per millimeter cube of blood. Leukocytes, which are about 5,000 to 10,000 per millimeter cube of blood, and this is about 1% by volume again. And erythrocytes, or red blood cells, which are about 5,000 to 6,000 per millimeter cube of blood, and about 42 to 47% by volume. So what you are seeing here is that blood is really a very diverse component with a lot of different sizes of these cells, whether it is red blood cells or leukocytes which are flowing around. And so therefore can we really use microfluidic principles for separating the blood flow. So as you know, as we have been talking about before, that there is a parabolic flow profile which develops in channels which have fixed or static walls on both sides, and the flow within is driven by a pressure gradient, a constant pressure gradient. So let us suppose you have a parabolic profile. So you have a channel here and you have a parabolic profile like this. So obviously it means that more towards the center the velocity would be more, and there would be a zero velocity or a zero slip on both ends. So therefore from side to center the V should actually continuously reduce, okay. And if suppose you have a case where you are flowing through this end through a pressure driven flow, a bunch of different cells immersed in a solution, one which is bigger, another which is smaller, then what do you think will happen? The bigger cells would try to move towards the edges by the principle of conservation of momentum, because the velocities that they will encounter by doing so, the edges are much smaller in nature in comparison to the velocities at the center. So automatically by the principle of conservation of momentum there would be a tendency of these bigger cells to kind of marginate towards the sides, smaller cells to come towards the center. This is actually a principle which happens inside the human body also, particularly for leukocytes. This principle is known as leukocyte margination, because of smaller sizes of the capillary and the flow of different constituents using a pressure driven flow. The pressure is created by the heart within the human vasculature system, and because it is a pressure driven flow, there is a tendency of the leukocytes to marginate by virtue of their sizes and go more towards the edges of the vasculature, and in comparison to the red blood cells, which kind of get accumulated more towards the center. So if I can actually biomimetically represent this in terms of a microchannel, let us say like this, and then we pull out different branches of these microchannels. Let us say this is a branch which you are pulling out here at this particular end. So you have to ensure though that this has a size based selection, and it only selects the size of the leukocytes. So the size of this channel is pretty much that of the leukocytes. So what would happen is that these leukocytes, which have already marginated, you can see these by these white cells here, and they are more abundant towards the side than in somewhere in the center, and of course the red blood cells are more abundant towards the center. So you can actually pull this out by designing a channel which is of the same size as this leukocyte is, and so you can make leukocyte rich samples by this kind of a separator. Okay, there are a lot of uses for this technology. Normally leukocytes are separated from the human blood by a process called a Buffy-Coat process, where you use a density gradient causing agent like fecal plaque to kind of make a density of different sizes of the cells, okay, within a solution. This is an assay which can actually replicate that Buffy-Coat process, which is too intensive both in terms of labor as well as contamination prone. So here with the small assay you could have a rapid throughput where you can get really a leukocyte rich sample towards the end collection here, in this particular case of the smaller channel. You could investigate that for further purposes. So these are some of the wonders that microfluidics can do to different systems and processes. So I would like to now actually go into a little different domain of microvalves. When we are talking about microfluidics, a very important mechanism that we must ascertain is control of fluidic flow, and for doing that we need to design different valving systems which can actually stop or block or gate the flows running past these small channels or capillaries, and also would be able to meter or control the flows in the flow rates that we desire in certain sections of a particular microchip. So microvalves are definitely used for those purposes. They are one of the most important components of a microfluidic system. So what all is important for valve designing? You have to consider the size of the device. These MEMS devices are very, very small. You have to consider pressures which are very, very high. That is why most of the pressure sources sometimes are off chip. Okay, the mechanisms of valving involves energy sources or pressure sources which are not on the same chip. We should be aware of biocompatibility issues if we are designing valve materials or choosing valve materials. The valve should have a proper response to the flow processes, and most importantly microtechnology should be used for fabricating such microvalves, particularly for using or gating the flows in micro scale. Okay. So valves can again be depending on the mechanism of their closing or working can be classified into passive or active microvalves. Okay. So passive valves can be like check valves, where by virtue of a change in property of a material, maybe it swells and blocks, the valve swells and blocks, or alternately by motion of fluid. Let us say you have a one directional valve from one side to another, or the pressure generated from one side to another, the valve closes one side automatically and opens when this pressure reverses back to the other side. So they are passive valves, okay, where there is no mechanical energy or any other form of energy which are used for operating these valves. So they are like check valves. Okay. Passive valves are normally a part of micro pump. Okay. We will study this micro pump topic in more detail later. So active valves on the other hand are essentially those which are dominated by some kind of energy input to the valving system. So, an active valve is a pressure containing mechanical device normally used to modify the flow or stop the flow or cease the flow. Although it can be mechanical as well as non-mechanical, there may be instances where you can use electronically to close a particular channel, or electrochemically to close or gate a particular channel, and we will actually consider some of these illustrations and designs later on where we design these different valving techniques. So, the working state of a valve really as you can see here is determined by a closure element or the valve seat over which this closure element would typically sit for the valving to be on, and this is driven by an actuator. Okay. So, that is how the valving process can be done in case of micro valves. Okay. So, some of these micro valves again can, based on what their initial states are, whether they are normally open valves or normally closed valves, can be classified into these two subtypes. Okay. Or a bistable valve which can close and open actively their valve seats. So, you have three categories here: normally closed, where valve normally after actuation opens up; normally open, where the valve actually is normally open but it closes on actuation; and bistable, which can also which can actually close and open both on some active energy being pumped in the valving system of the valve seats. So, valves can further control flows either in an analog manner or a digital manner, which means digital is just an off and on kind of mechanism. You have the fluid flowing at one instance and not flowing at another instance, whereas in analog mechanisms it is actually a slow closure of the valve and slow decrease in the flow rate across a valve and vice versa. So, you can categorize them into an analog way and a digital way. So, as I illustrated that in an analog valve at constant inlet pressure, the valve actuator varies the spacing between the valve seat and the valve opening, and this changes the fluidic resistance and thus the flow rates. So, it is a analog control on the rates. On the digital mode, however, there are only two valve states, fully open and fully closed. Okay. It can be operated in a pulse, actually with pulse width modulation technology, and here the open time is controlled, and hence the flow can be varied proportionally to what the open time is. So, essentially if you look at some of these output responses, this is again what an analog valve would typically look like. This is the discharge rate versus time, the plot of that. So, with time, as you see, as the valve is fully open, the flow rate is maximum, and it now closes and the flow rate goes down slowly, but then there is an analog response. So, there is a slow convergence of the flow rate to a maximum and a slow convergence of the flow rate again to a minimum. It is not a rapid one shot close and open phenomena. This is the digital micro valve again, where you have only two states, the close or the open, and then the interconnection between this is really very small in time. So, you do not need much opening time or closing time, it automatically either opens or closes. So, here this is a normally open system, this is a normally closed system. Okay. This is a normally closed, this is a normally open system. And by pulse width modulation, what you mean is you can actually use this technology to vary the flow according to your own interest. So, if you have more open time here, as you are seeing, the small loops that this discharge is formulating is the open time. Okay. So, this is a smaller open time, this is a slightly larger open time, this is a slightly this is the largest open time, and similarly these are the closure times, the time for which the valves are closed, and you can see there are all different times of closures. So, pulse width modulation basically would mean that if you have the pulse width to be more in case in this particular case you have the flow going on for a longer amount of time. So, pulse width modulation effectively therefore means that if you increase the open time, the flow rate would be more; if you reduce the open time, the flow rate would be less, and that way you can have a differential flow rate, okay, Q with respect to T. So, active micro valves again are characterized on the basis of their actuation principles. The actuation can be or actuation actually means the way that you are delivering the energy. You can actuate a micro valve pneumatically, You can do that thermoneumatically, thermomechanically. You can also use a piezoelectric crystal to actuate a microvalve. You could use an electrostatic method for microvalve actuation, electromagnetic, electrochemical, capillary force, surface tension, all different kind of forms can be used for actually closing and opening a valve system. So if we look at some aspects of microvalves and the way that you have to specify or characterize these systems, you have different parameters which you use for finding out the performance criteria of such valves. One is the leakage ratio. Okay. So the leakage ratio essentially can be represented as the flow rate of the closed system divided by the flow rate of the open system. Okay. So this is the fully open mode, what is the flow rate, and this is the fully closed mode, what is the flow rate. So there is a ratio between what is the flow rate at the closed mode in respect to what is the flow rate at the open mode. So basically this kind of represents the how what kind of leakages the valve would have. If this ratio is more than 0, that means definitely in the closed mode the valve is leaky. There is some flow which can be a fraction of the fully open flow, okay, and that fraction effectively cannot be done away with, and the valve would still be in its fullest operating and its most stringent operating condition would be able to let this flow past it or through it. So that is what leakage ratio would mean. Okay. This is Q dot closed is flow rate with the valve closed, and Q dot open is the flow rate with the valve, the pressure head that is actually driving the flow through this valve, okay, or the under root of or the square root of the pressure head that is driving through this particular valve. Let us illustrate this a little properly. So, therefore valve capacity C, let us say, of the valve is defined as Q star maximum, this is the maximum flow rate, divided by root of delta P maximum, which is the pressure difference across the valve, divided by rho g. Rho is the density, g is the acceleration due to gravity. So therefore this really is an indication of what is the pressure height, what is the height available, you know, causing the pressure gradient, what is the height of pressure that is available across both ends of the valve. And so the ratio between the maximum flow rate times and the root of this particular available height is what makes the capacity, or what defines the capacity of the valve. So therefore if the pressure head that can be withstood by this system is more, the valve capacity is lower, and vice versa. If the pressure head that can be withstood by this system is higher, the valve capacity is higher. Okay. So the closing force depends on the pressure range generated by the particular actuator sequence. Here in this particular illustration you can see some of the different actuation mechanisms and the way that pressure range can be generated by different actuator mechanisms. So here for example, okay, so let me just write these things down. Q dot max is maximum flow rate, delta P max is maximum pressure drop, rho is the fluid density, g of course as you know is the acceleration due to gravity. So for electromagnetic, disc type piezoelectric, electrostatic and electrochemical actuation, the pressure ranges that can be generated by this actuator in roughly about 1 to 10 kilopascals. If you go a little bit higher to pneumatic, thermoneumatic, shape memory, alloy based and thermomechanical actuators. The pressure ranges would be in the range of about 100 to 1000 kilopascals, and the highest pressure range that can be actuated is given by the stack type piezoelectric crystal, where there are multiple piezoelectrics which are stacked one on another, and the effective pressure that is felt is a result of the series pressure of all these different piezo crystals taken together. And here the actuation pressure can be as high as about 10,000 kilopascals. Okay, so that's what essentially the valve capacity would characterize. So therefore, what it means is that the maximum flow rate which it can hold per unit pressure head available is what the capacity is. So therefore, if suppose the pressure head is let us say fixed, and you have a valve which can hold let us say 1 centimeter cube per minute of flow rate, another which can hold 10 times this value, so 10 centimeter cube per minute flow rate. So for a similar kind of pressure head on both ends, C valve, the valve capacity would be much more in case of the 10 centimeter cube per minute flow closing valve in comparison to the 1 centimeter cube per minute flow closing valve. So that is what valve capacity is characterized as. So there are some other performance factors which include what kind of power is consumed by the system. Okay, what are the closing forces in terms of pressure ranges which you need for the valve to fully close, what kind of temperature ranges you can use the valve in. So these are some of the specifications if you design such valves. What is the response time? It is a big criteria, how quickly the valve can open and close a particular flow. Is there any reliability issue, or the valve operation is perfectly unique or not every time, or repetitive or not every time, is what is a very important design paradigm. Biocompatibility aspect itself of the material is a very major concept which is important for designing or selection of materials which would make these microvalves. And then finally, chemical compatibility again is a highly important parameter for designing the specifications of these microvalves. Let us do some now some real examples of valve designing to see a little more of how this can really be designed for flow systems. So the power consumption of the valve really is the total input power of the valve in its active power consuming state, and it may be small for electrochemical valves and very large for thermopneumatic valves, depending on what is the actuation mechanism and how the things can be actuated. So in this particular example here, we want to design a pneumatic microvalve system. So let us suppose, let us now solve this example of designing a pneumatic valve system. So we have a pneumatic microvalve here which has a circular silicon membrane. So this right here is the membrane which is circular as seen in the top view. This is the side view, the cross sectional side view actually. So the silicon membrane essentially is the valve seat in this particular valve, which means that if the silicon membrane kind of bends and deforms like this, it kind of blocks the particular valve. Okay, the valve seat is actually just below this membrane. So normally it is flat, it bends and blocks the entry of the airflow into the system. So the membrane is about 20 microns thick, it has a diameter of about 4 mm, 4000 microns, and the valve is normally open. Okay, so there is no pressure over this particular region here, and it is as if the valve is open at the very outset. Okay, and the gap in that particular case is about another 20 microns between the membrane and the valve inlet. So you have to determine the pressure required for closing the valve at an inlet pressure of about 1 bar. As you can see here, the opening diameter is 200 microns, which is right here. So we have to assume that the load is distributed on the valve membrane, and there is a Poisson's ratio of about 0.25, and there is a bulk Young's modulus of silicon which is about 170 gigapascal. So we have to design the system. So let us actually look at how we will design this. So for a small deflection, the spring constant of the valve membrane can be estimated as K equal to 16 pi E tube by 3 square minus 1 minus nu square. Now, this comes from a simple beam theory, and any standard mechanics of solids textbook would be able to demonstrate how the spring constant in case of thin beams can be reported. Okay. The various parameters are E is the Young's modulus, T is the member thickness, the member which is deforming and is really the valve, R is the radius of the member, nu is the Poisson's ratio. So, we have pretty much everything among this. So, let us calculate what the K value would be. It is equal to 16 pi times of E, which is 170 10 to the power of 9. The Young's modulus for silicon is 170 gigapascals. So, this is pascals times of thickness cube. So, it is 20 10 to the power minus 6, 20 microns is the thickness of the particular member in question. So, cube of thickness divided by 3 r cube, r is basically 4000 microns or 2000 microns. So, it is about 2 10 to the power of minus 3 meters. Cube of this times of 1 minus square of this times of 1 minus nu square, nu is 0.25 Poisson's ratio. So, this comes out to be effectively equal to 6.08 in 10 to the power of 3 Newton per meter. That is what the K value is. So, let us assume that the microvalve is closed at an actuation pressure of P ACT. So, let us assume the microvalve is closed at P act actuation pressure. Okay. So, the force balance equation for this valve, because it is a distributed load, is basically the actuation pressure, which is actually from this side, as you see here, this is the P actuation, okay, and this is the P inlet, all right. So, you are left with P actuation times of area of membrane times of P inlet times of area of the open system. So, essentially in this case the open system is nothing but the area of the membrane itself again. So, P input times of A open, okay, plus the spring force. Mind you, the pressure here is actually being resisted by this downward spring like movement of this valve. So, whatever force this P input would have on the membrane plus the force spring is essentially equal to the actuation pressure times the area of the particular membrane. So, this is essentially at equilibrium. This is at equilibrium, okay. This right here is an equilibrium. So, this right here again is the A open, the area of cross section which is open. So, equilibrium means that the membrane is fully seated over the inlet hole, thus valving the flow, and A open is the area of the inlet hole, P input is the inlet pressure, and that plus the spring force is essentially equal to the force by the actuation pressure on the other side of the membrane. Just about when the actuation begins, this equation slightly modifies. So, you have now P act times of m on one side, which is also equal to P in times of Am on the same membrane, because it is in the open position, plus the F spring. Spring force is still there, okay, when actuation just about begins. Okay, sorry, already written this thing back on the top, when the actuation just about begins, as you can see here. Okay. So, let us actually calculate some of these values. Let us see what happens when the actuation begins. So, you have P actuation pressure needed is P inlet plus F spring times 1 by Am. Am essentially is pi r square, r is about 2000 micrometers, and so therefore, the actuation pressure would be 10 to the power of 5 pascals. So, the pressure in the inlet side is about close to 1 bar, which is nothing but 10 to the power 5 pascals, as you know, plus the force spring, which is 6.08 10 to the power 3 times of the deflection, which is again about 20 10 to the power of minus 6. That is essentially the 20 micron displacement that would happen here, as you see. Okay. Let us assume that the port has not yet blocked, and the pressure is released onto the entire lower surface of the seat membrane, and this divided by Am, which is pi r square, r is 2 10 to the power of minus 3 square. So, this value comes out to be about 109,677 pascals. Now, when at equilibrium though, this paradigm changes. So, when at equilibrium, the P actuation needed would be much lesser. More so because now the active area over which this 1 bar pressure is available is only this little area here, that is the P, the area of the opening. Okay. So, let us see what that would be. Force spring in this particular case is again K times of 20 10 to the power minus 6, and P actuation times of pi times of P actuation times of pi times of 2 into 10 to the power minus 3 square would effectively be equal to 10 to the power 5 times of pi times of 0.1 10 to the power of minus 3 square plus 6.08 10 to the power 3 times of 20 times of 10 to the power of minus 6, and P actuation here would come out to be effectively equal to 3.1. Okay, so let me just write down the final value here. So, it comes out to be about 9581 pascals. So, in comparison to the earlier value here, which was about close to 109,677 pascals, this has reduced to almost 2 orders of magnitude and become about 9581 pascals. So, why that is so again? Because when the valve is open, the area of membrane or the area of inlet pressure or area available to the inlet pressure is the full lower area of the membrane. Okay. And when the valve is closed, the area available is only the inlet or the opening of the piping. Inlet piping. So, that is primarily the reason why the actuation pressure in the second case, where the valve is closed, is much lower in comparison to the actuation pressure in the upper case. This is though an advantage, because being at the micro scale, the area of cross section of such valves is very small, and so effectively the amount of force that is generated by the inlet side by design, which is also pressure into area, by virtue of the area being very small, remains small, and it necessitates a lower amount of actuation pressure. So, therefore, in case of pneumatic valves in this kind of configuration, it is always desired to make the inlet side opening as small as possible, which can rhyme with the microsystems, and that can help us to have lower amount of actuation pressures to control the valving action. If we design the same valve with a thermonumeric perspective, that means whatever this load, distributed load here was obtained, okay, on this particular membrane is done through heating some kind of a gas entrapped over the membrane, so that is called a thermoneumatic system. So, therefore, on a fixed volume, if you actually keep on adding electrical work or energy, there is an expansion of the gas which would cause a pressure to develop, and that pressure would be good enough for the membrane to bend and valve the inflow of the air, and so those systems are known as typically thermonumeric systems. So, for a similar kind of arrangement, let us see what would be the amount of temperature that is needed to be reached for sufficient amount of actuation force to be pressure to be generated, so that the closing action of the valve takes place. So, let us suppose you have the valve described in the earlier example, and this is designed with a thermonumeric actuator on the top of the membrane, and it is given that the actuator chamber is cylinder with a height of about 500 microns, and this is sitting on a diameter of about 400 microns, which is also the outside diameter of the valve, the silicon membrane valve, which is in consideration right now. So, if the chamber is filled with air and hermetically sealed, we have to determine the temperature required for closing the valve at an inlet pressure of about 1 bar, and the initial pressure and temperatures in the chamber are 1 bar and 27 degrees Celsius. So, again we use the Charles law. On a fixed volume, you have pressure kind of proportional to the temperature. So, therefore, T1 by T2 is temperature in the beginning by temperature after the expansion has taken place is pressure 1 by pressure 2. So, assuming the volume of the chamber is constant. So, here of course, the pressure, inlet pressure is about 1 bar, and we found out that the amount of pressure that is needed from the actuation pressure that is needed from the opening to the closing position or opening position is about 109,677 pascals. Okay. So, this is the P1 which is needed, and the inlet pressure P2 is about 1 bar, which is about 100,000, and so therefore, if the inlet pressure 1 bar is at 27 degrees Celsius temperature, which is about corresponding to about 300 Kelvin, we find out from this relationship that T2, or the temperature required for the pressure to be 109,677 pascals, is about 329 Kelvin, which is close to 56 degrees Celsius. So, therefore, you have to really heat the constant volume of the cylinder with a height of 5,000 microns, 500 microns by to almost about 56 degrees for the valve to self close using thermonumeric means. So, that is how you design a thermonumeric valving system. Okay. So, there can be also passive valves, as I recorded in my last lecture, and these passive valves essentially are based on either the expansion of a structure, blocking of flow because of this expansion, etc. So these valves are very beautifully illustrated by Bebe et al. In this particular paper reported in PNAS, where he used hydrogels, and essentially as you see here, these hydrogels are fixed to certain fixed members in a flow channel. So direction of flow being from direction A to direction B through this channel. So typically these are unexpanded, and you have a gap in between here from where the flow can go from A side to B side. But hydrogels are essentially things which expand or swell on different pHs, particularly when the pH is more like acidic, the valves would swell in volume. Okay, so it will expand. So if you have these valves expanding in volume, they become this big, and by virtue of their size they can block the flow. Okay, so now the flow is blocked because these hydrogels have kind of swelled, and they are blocking the flow direction in this particular channel, as a result of which these valves can be very good pH sensors. So small change in pH can result in swelling and flow stoppage of the particular valve, and you can calibrate the change of pH to the volume of swelling, or the volume difference that the valve would make by swelling, and therefore the volume of flow past the valve can be calibrated to the corresponding pH. So here, of course, as you are seeing, you can reversibly change the orientation by flowing back a basic pH, so that the valve kind of shrinks and gives way or opens the flow. And these being made up of hydrogel and soft materials, they can be biomimetically patterned. They are based on some of the flow valves that our heart probably possesses, where expansion and contraction keeps on either confining the blood onto the chamber of the heart or releasing the blood at a certain pressure. So this kind of brings us to an end of this particular lecture. In the next lecture, we are going to talk about some other valving mechanisms, particularly non-conventional mechanisms like electrochemical or surface driven valving or flow closing mechanisms. So with this, I would like to close this lecture. Thank you.